Potentially you could run into an issue in count 3. Until then, I don't think you need to worry about it. Unless you would like me to put one on the test like that. No, okay. Kelsey says no, so we're not gonna do it. Other questions? All right, so as two waves come together, so if I got a wave, just think of a transverse wave and I got it, it's moving along this way, and I got another wave coming like this, heading towards it. What happens when the two waves meet? Yep. So I got some sort of baseline here, and when they meet, recognize that this represents something that has pulled this thing up. Over here, I got something pulling this up, bless you. When those two meet, both pulling in the same direction, should be pulling higher than it did before. I got this pulling up here. I got this pulling down. When those two meet, well, I got this conflict here. They're going to sort of neutralize each other. Not necessarily completely, but depends upon the size of these waves. But if I have them going in opposite directions, you end up subtracting. Or adding a negative. If you get bigger, if the combined is larger than the individuals, this is constructive interference. If the combined is less than either individual one, what's the opposite of constructive?
Destructive.
Yep. If it's less than, if the combined is less than either individual, destructive. We'll assume it says interference. So as an example here, I took two waves that were very close to each other. And hopefully you can see that there are two different waves there oscillating back and forth. They are slightly different. If you look at the end here, they both start at 0, but look at the end, this one bottoms out right before it ends, and this one is still on the way down right before it ends. So they're just slightly different from one another. So I combine them, get them starting at the same spot. And I'm going to trust your eagle eyes here. They start at the same spot, and they seem to be in sync here, but by the time we get over here, there seems to be, gets a little bit farther apart. And I'll walk around just so that you can see that they're just a little bit farther apart. So they're pretty much in sync here, getting farther, splitting as we go. So in sync, close to in sync, and then they start getting farther and farther apart. In sync, farther apart. Making all three at the same time, so they start out in sync, and then they start getting more and more apart. So again, start at the same place, and they start splitting. So if I add these two waves together, except for the water damage, it looks like that if I add them together. It looks like I got a whole new different kind of wave here. Those had an amplitude of 1. Ooh, another word I forgot. Amplitude of 1, so when I add them together, it got an amplitude here of near 2. And it just starts getting smaller. If I extend it, it looks like that, or that. We start out with an amplitude of 2, they combine, It's constructive interference, destructive interference, and then it starts getting bigger again. So the combination has its own frequency. So if I combine a 440 hertz well, that's hopefully that's not kicking in over there. I just forget how slow these machines are. Just wait, they're getting everything ready for me. It might take several minutes. All right. So if I have 440 hertz is one frequency. So this means that the cycle's happening 440 times per second. And I have another thing that's 439 hertz, which means that's happening 439 times per second. So very close to each other. So we'll call this frequency 1 and frequency 2. The combination, if I play them at the same time, I get what are called beats. And so this will end up with something known as a beat frequency. I just got spoiled now. All right. All right, here's 440 hertz if the sound works. I assume everyone heard that. Here's 439 hertz. Could you hear the difference? So occasionally I do have students who have good enough ears that they can't hear a difference there. Oh, here's 430. God, we will do it this way. $440, 439. I can, but I don't have good hearing. Could you hear the difference, Dulce? You have that look like you almost. All right, let's play them at the same time. I'm going to start with the 439 because that's the page I'm on, and then I'll go to the other one. 439, 440. That wah-wah sound, that is the beats. Here's the complicated math behind figuring out what the beat frequency is. So we're going to find out that's the beat. 440 minus 439 is 1. There we go. There's the complex math. Just take the difference. Now, we can check to see if that beat frequency is indeed 1 hertz, because I know that the frequency, the reciprocal of the frequency is just the period. So what's the reciprocal of 1 hertz? Give me units.
Seconds.
Yes. So we should be hearing it getting really quiet once per second. If I did 439.5, so they're even closer together. So 440 hertz, 439.5 hertz. My beat, what's my beat frequency?
0.5.
So what's the period?
0.5 seconds. Oh, 1 divided by 8, right?
Yes, 1 divided by 0.5.
It's 2 seconds.
Yeah, 2 seconds. So the closer we get, the farther apart the longer it takes to complete the cycle. So here's 439.5 and 440. 1001, 1002, 1001, 1002. And back when they were piano tuners, and I assume there still are for the people who still play piano, but you basically, if you're trying to get a string to be vibrated at the right frequency, you're either going to tighten it or loosen it, and you play a pitchfork. You think a pitchfork, play at a certain frequency, and then you play the note on the piano, and you're listening for the beats. Probably helps to have good hearing too. All right, questions to hear? All right, building on the excitement, what we're going to do next is we're actually going to do the centripetal motion lab. We're going to head down to the lab room, and I can get the labs that should be printed out, and I'm going to take a look at your 2 labs to see what I did wrong.